Okay, so in this video we begin our study of Chapter 3 in your book, which will extend our knowledge of 1D kinematics to motion in 2D and 3D. Now recall that there's no actual physics being studied as of yet. We're simply building a mathematical framework, or language if you will, to describe and relate the many attributes of the various types of motion that we need to consider. Now in this video we will discuss sections 3.1 and 3.2 of your book, which covers the topics of vectors and vector operations. Let's go ahead and begin. Now, there are hundreds of different kinds of physical quantities that we can use to describe and measure various aspects of our world. However, these quantities can be grouped into two very general categories, those of vectors and those of scalars. Now, vectors are directional quantities. They have a magnitude or size to them, but they also have a direction. They can be pointed or oriented in different ways. Let's take a look at a few examples that illustrates this. In our first chapter, Chapter 2, we talked about this displacement quantity. Displacement, we said, was a vector. If I were 5 meters away from the origin, I would need to tell you which way that 5 meters was in relation to the origin in order for me to identify that position. We need both a magnitude and a direction to describe that. We also talked about velocity and acceleration. Now, when these two vectors are aligned in the same direction, we know the object speeds up. When they're in the opposite direction, the object slows down. As we consider now 2D and 3D motion, these vectors could be oriented at right angles to each other. They could be oriented at 30 degrees to each other. The direction of these two vector quantities in relation to each other determines how the object behaves. We have to consider that directional portion of those quantities. Other things that we'll look at: forces and momentum. These are certainly staples of physics. These are directional quantities as well. Now, the direction becomes pretty important, as illustrated by this picture. This person is pulling on a door where it says push. It doesn't matter how hard they exert that force. If it's not oriented inward, it's simply not going to open that door. Now, scalars, in contrast, have only a magnitude associated with them. They're quite a bit easier to work with. Some examples from Chapter 2 that we talked about: distance, speed, and time. And of course, other things that we could look at: mass, temperature, and energy. The list is quite extensive. This is by no means a complete list. But scalars have only a magnitude, no direction. Now, oftentimes we will use arrows on our diagrams to represent vector quantities, and the reason for that is quite simple. The arrow has a length associated with it, and that length represents the magnitude. And of course, every arrow has an arrowhead, and that arrowhead represents the way that that vector is pointed. Right? So arrows are very useful as vector quantities on diagrams. So now we consider what we mean by vector operations. When we add or subtract vectors, we have to consider which way those vectors are pointed in relation to each other. Now, that's pretty simple in 1D. When we add vectors in 1D, it's simple addition or subtraction, all that's needed. You do have to be careful about the signs, as the figures to the left here indicate. If I add an 8-kilometer displacement to a 6-kilometer displacement and they are aligned in the same direction, the resultant would be 14 kilometers. If however, I add 8 kilometers to 6 kilometers and they're in opposite directions, we see the resultant is 2 kilometers. Again, simple addition or subtraction is all that's needed there. Now, if the motion is in 2D, it gets a little bit more complicated, but still not too bad. Let's say this person starts down here at the origin, walks 10 kilometers towards the east, and then turns towards the north and walks another 5 kilometers. Now, certainly they walked a distance of 15 kilometers. That's a simple scalar addition. If I wanted to determine their displacement, how far they are from the point of origin, both as a magnitude and a direction, I might consider this a triangle that we have here. So if the actual travel paths are at right angles to one another, we can find the displacement by using the Pythagorean theorem. A squared plus b squared is equal to c squared. Well, in this case, I could say that d sub r, which would represent here the resultant displacement, is equal to the square root of the sum of the squares of those two displacements. So in this case here, that would be 10 squared plus 5 squared. That'd be 125. Square root of that is a little bit more than 11, and you can see that that is about the length of that vector. Now, if these things are at right angles to each other, we could also use tools from right angle trigonometry. SOHCAHTOA is a memory aid that I used when I was first learning trigonometry. It says that the sine of theta is equal to a ratio of the opposite side to the hypotenuse. The cosine of theta is equal to a ratio of the adjacent side to the hypotenuse, and the tangent of theta, the ratio of opposite to adjacent. So if I wanted to find the particular angle of that displacement, I would just use an inverse tangent function. Say that theta is equal to the inverse tangent of 5 kilometers divided by 10 kilometers, which would be about 27 degrees north of east. Now, adding the vectors in the opposite order gives the same result. This is the commutative property of addition. I see that if I first walk east and then north, I get to the same spot as if I had walked north and then east. So we can say that d1 plus d2 is the same as d2 plus d1. Now, even if the vectors are not at right angles to each other, they can still be added graphically by using the tail to tip method. And that's what I want to show you here. Graphical addition of vectors is a little bit labor intensive. We have to be very careful about drawing these vectors accurately. Usually we use a graph paper, a ruler, and a protractor to be able to get accurate results. And again, it does take a little bit of time, but nonetheless, it really does help build a visual of what we mean by vector addition. So if I wanted to add these three vectors together, I could do that using this method here. I might draw V1 on my sheet of graph paper, use a ruler and protractor to get the appropriate length and direction. If I want to add V2 to that, I just place the tail of that vector on the tip of the preceding, and then I could add V3 to that by just doing the same thing here. In succession, I can add any number of vectors this way. The resultant vector is a vector that points from the beginning of that sequence all the way to the end. It does have an arrow on it. It is a vector quantity. V sub r could be measured. Its magnitude could be found using a ruler. Its direction could be measured using a protractor. Again, somewhat labor intensive, but nonetheless, it's a good way to start working with vector quantities, and that's where we will begin. I'm going to save this slide for a separate video. It gets a little bit more involved, actually using a ruler and protractor, so you'll see that coming here shortly. Let's go ahead and finish up our discussion on section 3.2 by looking at an alternate method of vector addition, something called the parallelogram method. Here we place the vectors tail to tail instead of tail to tip. Let's do a quick review. If I wanted to add V1 to V2 via the tail to tip method, I take the tail of V2, place it on the tip of V1, and then construct a resultant from the beginning to the end of that sequence, as this diagram shows. If instead I choose the parallelogram method, I would place them tail to tail and then construct a diagonal of a parallelogram. As this diagram shows, the diagonal itself would then represent the resultant vector. We could measure its length and its direction as before. Again, we should expect to get the exact same resultant no matter which way we add these things. We just have to be careful not to mix the two methods up. For example, if I try to add them via tail to tail and then create a triangle like we do for this method, we would see that we get the wrong magnitude, we get the wrong direction. Clearly, this is an incorrect method of vector addition, so we got to be careful about mixing those two methods up. So why would we use the tail to tip versus the parallelogram? Tail to tip is really good for representing the addition of things that happen in sequence, so one after the other. For example, if V1 and V2 were displacements, they would occur one after the other. It makes sense to sort of draw them graphically this way. If, however, vectors occur concurrently at the same time, like for example, maybe forces acting on an object, we would typically draw them both originating on the object at the same time and then construct the diagram as a parallelogram so that we can see the combined effect of those two forces maybe occurring simultaneously. Again, these tools are really just here to help us visualize what's going on for a particular problem, so we just want to be able to get comfortable with drawing them, being able to interpret which way the net result is of the vector addition or subtraction, and that will help us sort of problem solve the problems as we move into the actual physics down the road. So there we go. That completes the video for section 3.1 and 3.2 on vectors and vector operations.